So the topic of this video is calculating probabilities of events. And I would like to start with reminding you some facts. For example, the probability value is the value between 0 and 1, where 0 is a probability of an impossible event, and 1 is the probability of event that is certain to occur. So basically, one refers to 100% probability, and 0 refers to, well, 0% probability. And so the probability is going to be a number between 0 and 1. It will never, these are called probability limits. It will never be a number less than 0, never be a number greater than 1. So because there is no such thing as the probability of 120, for example. Now, probability of an unusual event. We're gonna say that the event is unusual if the probability of that event is less or equal to 5% or 0.05 in decimal form. And as I already mentioned, we're going to use two different methods or two different approaches for calculating probabilities. We're going to use the classical approach and empirical approach. And we're going to use classical approach for the experiments where outcomes are equally likely, and empirical approach when the outcomes are not equally likely. So the first method that we're going to consider for computing probabilities is a classical approach. And here's the definition. An experiment has n possible outcomes, and each outcome is equally likely. Out of those, there are S of the outcomes that satisfy the description of an event E. Then the probability of the event E can be found as follows. S divided by n, where S is the number of ways a success can occur, and n is the total number of possible outcomes or sample space of an experiment. So let's consider an example. This is a quick quiz, consists of a multiple choice questions with 5 possible answers, A, B, C, D, and E, one of which is correct. If a question is answered with a random guess, find the probability that the number is correct. So we understand that the probability of a person randomly selecting A, B, C, D, and E are equal probabilities. Now only one is correct. So probability of event E, in how many ways a success can occur? Well, that's only in one. And how many total possible outcomes? 1, 2, 3, 4, 5. So the probability of success or event E happens is 1 out of 5. Now let's take a look at a base of the second way of calculating probability, and that's empirical probability, or otherwise known as relative frequency approximation of probability. And in order to use that, we have to collect the data or observe data and then use it for finding probabilities. And so the probability of success would be a ratio of successes that we observed divided to the number of trials that we inspected. So here's an example. In a study of 4,020 420,095 cell phone users in Denmark, it was found that 135 developed cancer of the brain or nervous system. And for question A, we're gonna estimate the probability that a randomly selected cell phone user will develop such a cancer. So we're gonna event C is a cell phone user develops a brain cancer. Develops cancer of the brain or nervous system. So to find the probability of event C, we're gonna figure out the number of successes, which in this case it was 135, divided by the total number of observations. And there was a total of 420,095 people in the study. And that probability comes down to 0.000321356. So I'm going to round it to 5 decimals. So that's the answer to question A. Let's take a look at question B. Is the result very different from the probability of 0.000340 that was found for the general population? I would say no, it's not very different. It's actually very close to that number. And then question C, what does the result suggest about cell phones as a cause of such cancers as has been claimed? So the general population had a result that's very close to the cell phone users. And if anything, the probability for cell phone users for developing cancer in cell phone users is less, right? Even though it's not conclusive, we're going to talk about the proper way to figure out for sure that the result suggests that there is less chance of cancer. But for now, we're just going to say they're close, and therefore it does not, there is no evidence that the cell phone users develop cancer of the brain or nervous system. All right, so in general, though, I want to come back to question B, where we found the results being not very different. So it's okay to say that for now, just by looking at the numbers, but usually if we are looking to find out if the results are very different, then we're looking for the difference of more than 5%. So 5% is going to be a common theme in a lot of things that we'll be doing. So the difference of more than 5% suggests results are very different. If it's less than 5, it's not very different. I wanted to show you another example, and it's gonna involve a different way of organizing the information. It says both parents have the brown-blue pair of eye color genes, and each parent contributes one gene to a child. Assume that if the child has at least one brown gene, that color will dominate and the eyes will be brown. Question A, list the different possible outcomes. And question B, assume that these outcomes are equally likely. What is the probability that a child of these parents will have the blue pair of genes? And what is the probability that the child will have brown eyes. Okay, so let's list all possible outcomes. We were told that basically we have two variables here, right? One gene comes from the mother and one gene comes from the father. So we have two variables, and usually when we have two variables, we organize that information in a two-way table, where on one side we're going to list one variable, and on the other side we're going to list another variable. So since both parents have blue and brown pair of eye-colored genes, so let's say this side represents the genes that come from them that mother has. So we have blue and brown. And this side represents the genes that father has, blue and brown. And then inside the table, we're going to have the genes contributed to a child. So what are the possibility? The first possibility that the blue gene is contributed from the mother, and also the blue gene contributed from the father. Then another possibility, brown gene from the mother and blue from the father. And then we continue filling the table. That's what we get. And then this is assuming that these outcomes are equally likely, what is the probability that a child of the parents will have blue pair of genes? Well, as you can see, there is only one case right here. So the probability that the child will have blue pair of genes is 1 out of 4. That's question B. Question C, what is the probability that the child will have brown eyes? Well, in order for the child to have brown eyes, he has to have at least one brown gene, because that gene is dominant. And we have 3 instances where the child has at least one brown gene. So the probability that the child has at least one brown gene is 3 out of 4.